So this is satellite laser ranging is one of the most fundamental space geodet techniques. Okay, the other one is VLBI. Satellite laser ranging provides the most accurate point positioning of all, so the most accurate. And the nice thing about satellite laser ranging, because it's point positioning, it determines directly a geocentric coordinates. Okay, so which means it is very good to determine, well, indirectly determine the location of the center of mass, which is the origin of the conventional terrestrial system, of any one of the International Terrestrial Reference System, which is just a different name for the same person. The other technique that is fundamental is VLBI, because VLBI give us the highest accurate baseline. Okay, so both working together is fantastic because they're fundamental, because one tells us about the location of the origin of the coordinate system, and VLBI give us the scale. Okay, and now GPS can provide both, but it's not as accurate. It's the difference is 1 order of magnitude less. So what satellite laser ranging does, or any laser ranging system, we have a cannon, laser cannon, and we actually can see during the evening, we can see the laser, well, the photons being transmitted. It is actually fascinating to see that. And this is a picture that I had opportunity to take in Germany when I visited a satellite laser ranging station. And and we have the receivers here. So this is a transmitter. This is the receiver. These they're connected to the same atomic clock, so they measure the energy that goes and comes back. Very weak signal that comes back. That is a process of reconstruction and then correlation. And the process of correlation will tell us when a particular wavefront was transmitted and then when was received, and then we compute very accurately the propagation time. And if you recall, then we divide the propagation time by, it's fine, I cannot change that. If we change the propagation time by 2 and multiply by the speed of light in the vacuum, we essentially get the why can I get this? Holy smokes, I have to leave. I cannot go back. Okay, that's fine. So the measured distance, P, is going to be the propagation time, delta T, okay, and divided by 2, multiplied by C. This is the basic measurement, and the observation equation, we connect the measurement with the geometry, okay? And of course, what we have in here, the geometric distance is nothing else but the distance between the, it is the length of the satellite position vector minus the receiver position vector. So the satellites, lunar satellite laser ranging satellites, they have their orbits very accurately positioned because they don't have, they're basically, the best ones are spherical, as we're going to see. So they don't have much atmospheric drag and not much solar radiation pressure. So we can then determine the coordinates of the receiver. It can be done both ways. Okay, we may, if you want to know the coordinates of the receivers, we will take the satellite orbits. If you want to compute satellite orbits, we have to constrain somehow the coordinates of the receivers. And now this is, of course, for one single pass. We can have one single station. We can have a network of stations and then have a big adjustment on the whole set of stations, okay? What this system does is that there are tens of satellites who have retroreflectors. So they're basically mirrors. And these mirrors are then used to reflect the laser. Okay. And some of the satellites are spherical and they just have mirrors. And so they're dedicated for satellite laser ranging. So these would be the best ones to do SLR. But there are other satellites then that would have a different shape. For example, some of the GNSS satellites, they have also retroreflector. So what happens that during a whole observation session, it is several satellites are observed because the satellites are very low. The satellite laser ranging satellites are low. They're low orbit satellites and they go faster. Of course, the GNSS satellites are typically middle Earth orbiting satellites, and they take several hours to go through. One thing that happens with satellite laser ranging is that, just a moment. Is that the there has to be some time control because of air traffic. Nobody wants the laser beam to hit our aircraft, not because you're going to destroy it, but it can blind the pilots. So in this case here, in this station is close to Berlin. So they have every day they have the they have to coordinate with traffic control to avoid shooting a satellite that is along the path of a of a jet. Okay, here I am. Oh, yeah. So it is nice because you start they start to operate during the day and you see nothing. And suddenly, as the night comes, the sunset comes, you start to see the beam growing until it gets very strong during the evening. Yeah. And that was in Germany, so they have good beer too. So anyway, it was a nice evening. Okay, so satellite laser ranging is a two-way ranging system. The mathematical model is like GPS, except for the clock offset. So the mathematical model for satellite laser ranging, a complete mathematical model, would be these would be the observation. This is the geometric distance. And we could still have a small time offset, but these would be actually to try to absorb some uncertainties. The other thing that would have would be correction for tropospheric delay. Okay. Also, ionospheric delay, because it is electromagnetic system going through the atmosphere. We're still going to have effect of troposphere and ionosphere. And then we could also have a term that would account for any kind of instrumental noise or measurement noise, instrumental noise. So this would be the a mathematical model for satellite laser ranging, in which we have observations from one side, we have R usually known, because we can think of satellite orbits known, receiver unknown, can be the other way around. We may have these as an extra unknown, and these are basically coming from models, and these would be basically noise, so would be dumped into the residual vector. Precision, 5 millimeters short-term bias stability, and 2 millimeters long-term bias stability. Okay, so here we are talking about if we are combining well, a month of sessions. Okay, but the thing is, we're talking about 2 millimeters absolute positioning. Okay, most accurate point positioning system, and it is basically used for scientific purposes because, let's face it, we are not going to carry a satellite laser ranging cannon with us, and not just because it's bulky, but it's of course very expensive. So scientific purposes, it provides a geocentric position and motions of ground stations, of course, because as time passes by, the station coordinates will vary because of plate tectonics. We can improve the satellite orbits. Okay, we can study the Earth gravity field and temporal variations. Because if we have a theoretical orbit, theoretical orbit, And when we have the actual measurements, we may see that the satellite will vary a little bit. Okay, so these will be the measurements here. So by looking at the difference between the theoretical and the real, well, not real, it's never real. It should be called measured eraser. And the measured orbit, the real would be there because we have both have uncertainties. So we're dealing with have to propagate the uncertainties with this thing. But so the difference between the theoretical and measured orbit will be due to mostly due to variations in the gravity field. Variations in the gravity field. So this is then used to study the Earth gravity field. We can also determine the Earth orientation parameters, position of the pole, instantaneous pole, and the rotation of the Earth. And we can also use as constraints for the studies of the internal structure of the Earth. So satellite laser ranging is more a scientific system than a practical system. And well, most likely you're going to read about it rather than actually use it. Okay, but at least you know the principles, and most importantly, it's a system that is unbeatable as far as point positioning or absolute positioning goes. The satellites that we have available, these are dedicated satellites. Okay, one is known as the LAGEOS, Laser Geodynamic Satellite. This satellite was launched in 1976. I have to tell you that the satellite laser ranging was one of the systems that killed the BC4 network, the one used in the measuring directions, direction observable. Okay, the first network, so that network, the BC4, was killed by satellite laser ranging, and also by Doppler system. So we have a LAGEOS one built by NASA, launched in 76. The other one is launched in 92. And what these things are, okay? These things are what we call cannonballs because they're small, okay? So 60 centimeters in diameter, but they weigh hundreds of kilograms. They are located close to the Earth, and one has a retrograde orbit, the one has a prograde orbit. Here is the eccentricity, and here is the period. Okay, so they travel very fast because they're very close. And they have 426 meters, essentially. Another satellite that is dedicated is the IGSI satellite. It's a Japanese satellite launched in 1986, and this is slightly larger, but it still has the idea of a cannonball because it's very heavy. It has the same objective, of course. It has mirrors and cube corner reflectors You can see Q corner reflectors here. Here we see a mirror. So there are different types of reflectors. Now, there was a discussion in the last International Union of Geodesy and Geophysics meeting, General Assembly, that someone said AGSI is not a good satellite laser ranging satellite, and I still need to inquire why the guy says. But anyway, it is used, and it is considered a dedicated satellite laser ranging satellite. Other ones, we mentioned about LEGIOS, AGSI, that is the French satellites, and these are the Russian satellites. And then there are shared laser satellites. So these are satellites that are placed in orbit for different objectives, but they have retroreflectors, which means they can also be used by laser ranging. NVSat, which is a remote sensing satellite, some GPS satellites, all the GLONASS satellites, Galileo satellites also have some of them, the Earth remote sensing system 1 and 2, TOPEX Poseidon. This is for satellite altimetry. So, which means how's it called? The satellite laser ranging is taking a hitchhike on these systems, and there is a long list. There is a long list. You can check the names that keep updated on this site here. These would be most common ones. So one interesting thing, just since I remember now, that if you have GPS and GLONASS satellites using retroreflectors, this is something interesting, because we may have a the laser system, okay, satellite laser ranging, and we may have also a GPS. This is not a person, this is a receiver. We also have the GNSS pseudo range, or even the carrier phase. So, which means that we can compare both systems. Okay, we'll have coordinates. Of course, you need to know the would have to know the eccentric position of the GNSS station vis-a-vis the satellite laser ranging. So there's going to be an error associated with it. But it is something nice, because you can have solutions for both systems from the same satellite. So that would call these a tie. Okay, so we'll be tying up GNSS and satellite laser ranging. That is a global network. That is a service from the International Association of Geodesy that's called the International Laser Ranging Service. And there are a number of satellite laser ranging stations. Okay, this map here is from, I didn't update this year, so this is from last year. I don't think that it will be different. We can see, let me just draw here the equator to highlight the spherical unbalance. We can see we have tons of stations in the northern hemisphere, okay, and we have just a few in the southern hemisphere. So, which means that there is going to be a bias that may affect the location of the geocenter. That's why usually you have the Z component when you do a transformation. The Z, the translation for the Z component is usually the larger value. So current sites, engineered sites, which I actually cannot see here in this, and we have inactive sites. So unfortunately, we have none in Canada. Canada has been disappointing as far as the space geodesy is concerned. And now we have the other one, which is the same principle, but measures the range based on measurements to retroreflectors that are placed on the lunar surface. The Apollo 11, 14, 15, so these are manned systems, and then the Soviets at the time placed retroreflectors using a unmanned system called Lunar. Objective is scientific, study the moon and Earth interactions, and the observations, the sessions will take several hours because the return signal is very weak. Distance to the moon is measured with an accuracy of 3 centimeters, so we can check the relative error of that. And there are 4 observatories that are capable of performing laser to the moon, so not a satellite laser ranging system is not necessarily capable to that. So we have one in Texas, one in France, one in Germany, and there is this one in Hawaii, which I believe is still closed. So it's funny because we don't have any in the US. We have in France, in Germany, and in Texas. Science, it's of course mostly used for science. It is going to give precise lunar ephemerides, so the direction to the moon, and study the internal structure of the moon. So internal structure, location, and the Earth-Moon interactions. Okay, so we can track how much the moon is getting farther away from us. Here is a snapshot of a retroreflector left by the Apollo missions. Now this is a picture of the of Hollywood, of course, but there are retroreflectors there. And this is a picture of the McDonald telescope. This is the position of the laser reflectors on the moon. Okay, so which means that when you are with your girlfriend or boyfriend or a spouse or anyone that you like, and you want to look at the moon, you can say, "Oh, I can show you where the retroreflectors are located." Okay, yeah. So okay, so this is a snapshot of laser ranging, the use of laser ranging for space geodesy. And we will stop here.